Hello, and welcome to the quiet cosmos. If you're fascinated by the wonders of the universe and the mysteries hidden in the stars, you're in the right place. Before we dive in, make sure to hit that like button, subscribe, and ring the bell so you don't miss any of our journeys through space and time. Now, I'd love to hear from you. Where are you watching or listening from? Are you stargazing in the quiet of your backyard, or perhaps tuning in from the bustling heart of a city? Wherever you are, know that the starlight you see tonight has travelled millions, even billions, of years to reach you. It's a reminder of how deeply connected we all are to the cosmos. So, as we explore the science of starlight, take a moment to think about the light that's been journeying toward you all this time, just like this video. Let's embark on a peaceful, awe-inspiring exploration of how light from the stars reveals the secrets of the universe, from the birth of stars to their final moments, and everything in between. You're in for a cosmic treat. Starlight, at its most fundamental level, is the universe's language, a cosmic message that stretches across vast distances, reaching us from the very stars themselves. It is through this light that we are able to decode the distant universe, interpreting the secrets of stars, galaxies, and everything in between. Starlight, in essence, acts as a bridge between the unknown and the known, carrying with it the stories of the cosmos that have travelled for millions, even billions of years. To think of starlight as a language isn't simply poetic. For centuries, human beings have looked up at the night sky, seeking answers, wondering what the twinkling dots overhead really represent. In ancient times, these points of light were the markers of seasons, navigation tools, and gods. Civilizations such as the ancient Egyptians, Babylonians, and Greeks used the stars to guide everything from agriculture to architecture. But over time, as our understanding of the universe grew, the stars began to reveal much more than mere patterns in the night sky. Through starlight, we could start to decode the deeper mechanics of the universe itself. The first steps in this journey were made by figures like the great philosopher and mathematician Pierre-Simon Laplace, who, in the late 18th and early 19th centuries, proposed groundbreaking ideas about the nature of stars and their life cycles. Laplace's work helped shape our understanding of how stars influence their surroundings, such as how they radiate energy and light, and how these emissions can reveal information about their composition, age, and even their eventual fate. He also speculated on the idea of stellar evolution, an idea that was truly ahead of its time. What Laplace couldn't know, though, was how much starlight could tell us about the very fabric of space and time itself. Fast forward to the modern era, and our understanding of starlight has grown deeper and more complex, thanks to the contributions of scientists like Albert Einstein and his theory of general relativity, which fundamentally reshaped our understanding of how light interacts with the very structure of space. Einstein's ideas suggested that light could bend, curve, and travel through the very fabric of space-time. This groundbreaking theory turned starlight into more than just a simple beam of light. It became a tool for measuring the curvature of space and understanding the very nature of the universe. In the 20th century, the advent of quantum mechanics added another layer of depth to our understanding of starlight. The discoveries of figures like Max Planck and Niels Bohr showed us that light is not just a continuous wave, but is also made up of discrete particles called photons. This quantum nature of light means that starlight carries with it much more than just energy. It carries information about the star itself, its temperature, composition, and even its motion across the sky. In fact, when we look at the light from a star, we are essentially looking at a snapshot of that star's history, frozen in time. As starlight travels through the vastness of space, it gathers information from everything it encounters. The photons that we see today from a star may have been emitted thousands, or even millions, of years ago. That means every beam of starlight carries the story of its journey through space, offering us a glimpse into the past of distant stars, galaxies, and nebulae. We can use that light to measure the distances between galaxies, to determine the speed at which stars are moving, and to understand the mysterious forces that govern the universe, like gravity and dark energy. This idea, that light is not just a way to see the universe, but also a means of understanding it, is a cornerstone of modern astronomy. The study of starlight, known as stellar spectroscopy, has allowed astronomers to unlock the secrets of the stars. By analysing the light emitted by a star, we can tell its temperature, its chemical composition, and even its age. The patterns of light, or spectral lines, reveal information about the elements present in the star's atmosphere. Each element absorbs and emits light at specific wavelengths, creating a kind of cosmic fingerprint that tells us exactly what is happening inside the star. But perhaps the most profound aspect of starlight is the way it connects us to the universe. When we look at the stars, we're not just observing distant points of light. We're looking at the very building blocks of the cosmos. We're witnessing the births and deaths of stars, the formation of galaxies, and the processes that have shaped the universe for billions of years. Starlight serves as both a guide and a messenger, offering us a glimpse into the deepest mysteries of space. It is no exaggeration to say that starlight is the key to understanding the cosmos. As we continue to explore the universe, every new discovery we make, from the detection of exoplanets to the study of black holes, relies on the information carried to us by light. Each beam of starlight, whether it's from a star in our own galaxy or from 1 billion of light years away, holds the answers to questions we've only just begun to ask. So, the next time you gaze up at the night sky, remember that the light you see is much more than just illumination. It is a message from the universe, encoded in waves of light, carrying the secrets of the stars to those willing to listen. When we gaze up at the stars, the light we see is far more than just illumination. It's a message from the heart of the universe, but the way we understand that message has been shaped by an incredible journey into the strange world of quantum mechanics. At first glance, light seems so simple. It's the brightness we see, the warmth we feel from the sun, the twinkling in the sky at night. But when we delve deeper, we discover that light is a phenomenon so fascinating that it blurs the lines between what we think we know and the unknown. To truly understand starlight, we must first understand light itself. For centuries, scientists struggled with the nature of light. Was it a wave, like sound or water, or was it a particle, like tiny grains of sand? The answer, as it turns out, is that light is both. This idea is known as wave-particle duality, and it was one of the cornerstones of the emerging field of quantum mechanics in the early 20th century. In the year 1905, Albert Einstein published a revolutionary paper that helped explain this strange behavior. He proposed that light, although it behaves like a wave, is also made up of tiny particles called photons. Each photon carries energy, and it's this energy that allows light to interact with matter. When light hits an object, such as the surface of a star, the photons can transfer their energy to the atoms, causing the atoms to move or change in ways that reveal information about the star's composition. This was a groundbreaking idea, but it was far from the only contribution to our understanding of light. Another key figure in the development of quantum mechanics was Max Planck, whose work in the late 19th century led to the discovery of what's known as Planck's constant, a fundamental constant that governs the energy of a photon. Planck's insights into energy quantization laid the groundwork for Einstein's later work, and together, their contributions helped scientists develop a new model of how light behaves at the atomic level. But there's more. As scientists like Niels Bohr began to explore atomic structure, they uncovered the fact that light isn't just emitted randomly by stars. Instead, the light we see comes from very specific interactions between photons and electrons in the star's atoms. When an electron in an atom absorbs energy from a photon, it moves to a higher energy level. When it drops back down to its original energy level, it releases that energy as light. This is why each element has its own distinct signature of light, what we call an atomic spectrum. The light emitted by stars is like a fingerprint that tells us exactly what elements are present, what their temperatures are, and even the star's velocity as it moves through space. But light doesn't just give us information about what's happening in a star at a particular moment. Thanks to the strange nature of quantum mechanics, light also carries information about the past. This is where things get truly mind-bending. When light travels across space, it carries with it the imprint of everything it's passed through. It can be altered by the gravitational fields of stars and galaxies, or by the density of gas and dust between stars. And when light encounters a powerful magnetic field, such as the ones found in the atmospheres of stars, it can become polarized, revealing even more details about the star's structure. Yet, quantum mechanics doesn't just shape how light behaves, it also raises some fascinating questions about how light interacts with the universe. One of the most intriguing concepts in modern physics is quantum entanglement, a phenomenon where particles like photons can become linked in such a way that the state of one particle is instantaneously related to the state of another, even if they are light years apart. Although this may sound like science fiction, quantum entanglement has been experimentally confirmed, and it suggests that our understanding of how light travels through space could be even more complex than we currently realize. It's possible that entangled photons could reveal new ways to study distant stars and galaxies, offering insights into the deepest reaches of space. Imagine being able to detect light from stars that is somehow entangled with the light from other stars, opening up a new way to observe the universe in ways we haven't even considered yet. And then there's the emerging field of quantum optics, an area of study that explores the interaction of light with matter at the quantum level. This field is poised to revolutionize how we study starlight in the coming decades. By using quantum properties of light, such as superposition and entanglement, astronomers could soon measure the tiniest changes in starlight with unprecedented accuracy. This could allow for the detection of previously undetectable phenomena, such as minute fluctuations in a star's brightness or the faintest traces of light from distant exoplanets. Quantum optics holds enormous potential for the future of starlight study. It may one day lead to the development of more advanced telescopes and instruments that can peer deeper into space than ever before. By studying light with such precision, astronomers could learn not only more about the stars themselves, but also the very fabric of space-time that surrounds them. In the meantime, the basic principles of quantum mechanics already help astronomers decode the light we see from distant stars. Every photon of light carries a wealth of information about the star it came from, its composition, temperature, age, and even its motion through space. When astronomers observe the light from a star, they can use this information to build a detailed picture of the star's life cycle. They can detect elements like hydrogen, helium, carbon, and oxygen, and analyze their relative abundances to understand the star's age and evolutionary history. By studying the shifts in light's wavelength, they can measure how fast the star is moving toward or away from us, a technique known as the Doppler effect. In short, starlight is not just light, it's a message from the heart of the universe, encoded in the very fabric of quantum mechanics. Every photon that reaches us carries with it a record of the star's past and a clue to its future. By unlocking the mysteries of how light behaves, we're able to peer deeper into the universe than ever before, uncovering secrets that have been hidden for eons. And as our understanding of quantum mechanics continues to evolve, so too will our ability to decode the starlight that illuminates the vast expanse of space. Stars begin their lives in some of the most mysterious and beautiful places in the universe, vast, dense regions known as molecular clouds. These clouds, often referred to as stellar nurseries, are made up of gas and dust, primarily hydrogen, that's so cold and thick that it feels almost frozen in time. The temperatures here are incredibly low, around minus 273 degrees Celsius, just above absolute zero. Despite this extreme cold, something amazing is happening in the heart of these clouds. As tiny regions within the cloud start to collapse under their own gravity, they begin the long process of turning gas into a star. It's in this quiet collapse that the first whispers of starlight are born. But before a star shines in full brilliance, it has to pass through a very important phase, the protostar phase. Protostars are like the universe's earliest versions of a star, still in the process of forming. They're surrounded by a hot, dense cloud of gas and dust that hasn't yet been cleared away. The heat from the collapsing gas starts to build up, but it takes time for this heat to reach the temperatures needed to kickstart nuclear fusion, the process that will eventually make the star shine. Even before fusion begins, though, we can already start to see the beginnings of starlight. In fact, the first light emitted by a protostar is quite different from the light we see from mature stars. This early light tends to be much dimmer, and often in the infrared part of the spectrum, something we can't see with our eyes. This is because the protostar is still too cool to emit visible light, but it's hot enough to emit infrared radiation, which is easier for us to detect with specialized telescopes. The starlight from these early stages is crucial because it provides clues to the conditions in the star-forming regions and the processes at play. The story of star formation doesn't end with the protostar. As the star continues to grow and the gas surrounding it clears away, it begins to shine more brightly. The energy that's produced by nuclear fusion in the core of the star pushes against the gravitational forces pulling inward, creating a balance that stabilizes the star. But what's really fascinating is how astronomers can use the light from these young stars, these first glimmers of starlight, to learn about the intricate details of the star formation process. Every speck of starlight, even in these early stages, holds information about the star's age, its mass, and the conditions under which it formed. As astronomers observe the light from these early stars, they rely on the work of several key figures who laid the foundation for understanding how stars form and what their light tells us. One such figure is Robert H. Dicke, an American physicist whose work in the 1940s and 50s on cosmic microwave background radiation helped establish some of the earliest ideas about the origins of the universe and star formation. Dicke's research, along with the discoveries of his colleagues, paved the way for the later understanding that stars are born from the coldest, most distant corners of space, only to eventually burn hot enough to radiate light across galaxies. While figures like Dicke helped us understand the broader picture of cosmic evolution, there are also lesser-known scientists who made profound contributions to our understanding of starlight and the star formation process. One of the most important voices in this field was Cecilia Payne-Gaposchkin, an astronomer whose pioneering work in the early 20th century radically transformed our understanding of stars. Through her research, Payne-Gaposchkin determined that stars are primarily made of hydrogen and helium, challenging previous assumptions that they were mostly composed of heavier elements. Her findings, published in 1925, were foundational in understanding how stars generate light through nuclear fusion. As stars like these evolve, they follow a well-established cycle. The first light we see from them comes from these early stages, when they're still forming and heating up. As time goes on, their light changes, and the stars eventually settle into the main sequence phase of their life cycle, where they burn steadily for billions of years. During this phase, the light we see is a direct result of the fusion occurring deep within their cores. The more massive the star, the shorter its life cycle will be, burning through its fuel much faster than smaller stars. These stars eventually evolve into red giants or supernovae, and their light will continue to offer astronomers clues about their past even as they die. The light emitted by young stars, often captured through infrared observations, helps us peer into the heart of star-forming regions, revealing the stages of evolution that would otherwise remain hidden. Because starlight carries information not only about the star itself but also about the surrounding environment, astronomers can learn a great deal from these early emissions. For instance, they can study how gas and dust interact with the starlight to learn more about the conditions that lead to star formation in the first place. This kind of research is ongoing and is fundamental in answering some of the most profound questions in astrophysics. What are the conditions that give rise to stars? How do those stars influence the formation of planets? How does starlight help us piece together the vast, intricate puzzle of cosmic history? As we look further into space with advanced telescopes, we continue to refine our understanding of star formation, using the starlight from young stars as our guide. The study of molecular clouds, where stars are born, and the starlight that emanates from these forming stars, is one of the most important fields in modern astronomy. Each burst of light from a young star adds a layer of knowledge, helping us better understand the early universe and the processes that have shaped it. So the next time you look up at the night sky and see a distant star, remember that its light has likely travelled billions of years to reach you, but that light is just the final shining chapter in a long story that began in the cool, dark clouds of gas and dust, where the universe's most precious objects, its stars, are born, grow, and eventually pass their light on to us. Imagine the power of a star contained in a ball of burning gas. Now imagine that power suddenly bursting forth in a flash of intense energy, like the sun throwing a tantrum. This is what happens during a stellar flare, a sudden, violent eruption of energy that can outshine an entire star for a brief moment. These bursts, although brief, are immense. They release as much energy in a few minutes as the sun emits in days or even weeks. Stellar flares are one of the most dramatic events in a star's life cycle, and they reveal a great deal about the dynamics of a star's atmosphere. At the heart of a stellar flare lies the star's magnetic field. To understand this, we need to think of the star not just as a ball of gas, but as an enormous dynamo. A star's magnetic field is constantly in flux, shifting and twisting as the star's plasma moves. In our sun, this magnetic activity is responsible for sunspots, dark spots on the sun's surface, and solar flares, which are just one type of stellar flare. The work of Eugene Parker, an American astrophysicist, helped us understand how these magnetic fields form and evolve. In 1960, Parker introduced the concept of the solar wind, a stream of charged particles flowing outward from the sun. He also described how these magnetic fields can interact in powerful ways, creating conditions where energy is suddenly released in bursts, creating flares. His work laid the foundation for understanding not just the sun, but other stars as well. What makes a flare so spectacular is how it alters the starlight we observe. When a flare erupts, it emits vast amounts of energy across the electromagnetic spectrum, from radio waves to X-rays. The visible light we normally see from stars is just a small part of this spectrum. When a flare occurs, it causes a temporary increase in brightness, often by a factor of 10 or more, over a wide range of wavelengths. This rapid increase in light is one reason flares are so interesting to astronomers. By studying how flares affect the starlight we see, we can gain insights into the structure and behavior of a star's outer layers, which are otherwise hidden from view. These bursts of energy don't just affect the star itself. They can have a profound impact on the environment around the star, especially if there are planets in orbit nearby. For planets that are close to their stars, stellar flares can drastically alter their atmospheres. The intense radiation from a flare can strip away a planet's atmosphere, a process known as atmospheric stripping, or it can heat the atmosphere to extreme temperatures. This could, in theory, make planets less hospitable to life. Even on Earth, the sun's solar flares occasionally affect our own atmosphere, causing disruptions in communication and navigation systems. Astronomer George L. Clarke was one of the early researchers who helped us understand the behavior of flare stars. These are stars that are known to frequently produce flares, often much stronger than those observed in the sun. Clarke's work focused on how these stars might impact nearby planets. He suggested that flare stars, particularly those that are unstable or in rapid rotation, could pose significant challenges to planetary habitability. Planets that orbit these stars might experience frequent powerful flares that could strip away their atmospheres or make them too hot for life to survive. This insight has led to important considerations when searching for habitable exoplanets. If a planet is orbiting a flare star, even if it's in the habitable zone where conditions are just right for liquid water, the flare activity could make it a less than ideal candidate for life. But not all stars are flare-prone, and not all flares are the same. Stars that are younger, smaller, or more active tend to produce more frequent and more powerful flares. For example, M-dwarf stars, the most common type of star in the Milky Way, are known to be flare stars. These stars are cooler and smaller than our Sun, but they often release enormous flares that could have a significant effect on any planets orbiting them. For life to exist on a planet around such a star, it would have to withstand these frequent bursts of radiation. Interestingly, stellar flares can also provide valuable clues about a star's internal processes. The way a flare forms, how the energy is released, and how it interacts with the surrounding atmosphere, tells us a great deal about the magnetic fields and the dynamics of the star's outer layers. By studying flare stars, astronomers can learn more about the physics of stellar atmospheres, which is crucial for understanding not just how stars behave, but how they evolve over time. Even though we observe flares as brief flashes of light, the energy they release is immense and can last for hours or even days. The most energetic flares are capable of releasing billions of times more energy than the sun's usual output. This makes studying them especially exciting. With the help of modern instruments, such as space telescopes and observatories that monitor X-rays and radio waves, astronomers are learning more about the physics behind stellar flares every day. In some ways, these flares are like the fireworks of the starry sky, but they are much more than just beautiful spectacles. They offer a rare and intense look into the fundamental forces at work inside stars. While we may think of flares as dramatic and exciting, they also present a challenge when we consider life on planets. If we ever find ourselves looking for signs of a life on distant exoplanets, we need to remember the role that stellar flares might play in shaping those planets' environments. Too much flare activity, especially from unstable stars, could make planets hostile to life. But in contrast, a star with relatively stable flare activity may allow life to thrive, assuming the planet is in the right zone and has the right protective measures, like a strong magnetic field or thick atmosphere. In the end, stellar flares are one of the many dynamic and energetic phenomena that make stars so interesting to study. They're windows into the turbulent lives of stars, providing insights into their magnetic fields, their atmospheres, and how they interact with their environments. But they also serve as a reminder that the universe is full of forces far beyond our control. Whether it's the flicker of a flare or the steady glow of a distant star, the starlight we see is a product of the incredibly complex processes that unfold in the heart of each star. And sometimes those processes are violent, sudden, and beautiful. As we peer into the night sky, we see the light of stars, a steady glow that reaches us across vast distances, telling the story of distant suns. But what happens to the light from these stars when they reach the end of their lives? The light we see today is just the final glimpse of a much longer and more complex process. Some stars, particularly those that are much more massive than our Sun, eventually reach a point where they cannot sustain themselves. When this happens, the star begins a dramatic transformation, culminating in the creation of one of the most fascinating and mysterious objects in the universe, the black hole. A black hole, by its very nature, is an object that no light can escape from. It is a place where gravity becomes so intense that not even photons, the very particles that carry light, can escape. This is where Starlight's journey takes an unexpected turn. When a star collapses into a black hole, the very light that once emanated from it is trapped, never to be seen again. But the process by which a star transforms into a black hole is both mysterious and deeply fascinating, and it begins with a fundamental concept known as the Chandrasekhar limit. Subrahmanyan Chandrasekhar, an Indian-American astrophysicist, introduced this limit in 1931. He discovered that there is a critical mass, about 1.4 times the mass of the Sun, above which a white dwarf star could no longer support itself against the force of gravity. When a star's mass exceeds this limit, it collapses under its own weight, and the result is a supernova explosion. For stars even more massive than this, the collapse continues even further, leading to the formation of a black hole. Once the collapse reaches a critical point, the star's core becomes infinitely dense, and the gravitational pull becomes so strong that it warps space-time itself. At this point, a black hole forms, and no matter or light can escape its grasp. What happens to the starlight from a dying star when it becomes a black hole? Once a black hole is formed, any light emitted by the star is drawn into the event horizon, which is the boundary surrounding the black hole. This is the point of no return, where even light cannot escape. All of the energy from the dying star, including the light it once emitted, is swallowed by the black hole. For all practical purposes, the light is gone, vanished into a region where not even the most powerful telescopes can observe it. However, just because light cannot escape a black hole, this doesn't mean that black holes are completely invisible. One of the most profound discoveries in modern astrophysics came from the work of physicist Stephen Hawking. In 1974, Hawking proposed that black holes might not be entirely black after all. According to his theory, black holes can emit radiation, now known as Hawking radiation, due to quantum mechanical effects near the event horizon. In simple terms, Hawking suggested that pairs of particles and antiparticles can spontaneously appear and annihilate near the event horizon. Sometimes one of these particles falls into the black hole, while the other escapes. The escaping particle is what we detect as Hawking radiation. Although this radiation is incredibly weak and difficult to observe, it has profound implications. For one, it suggests that black holes may eventually lose mass and energy over time, potentially leading to their eventual evaporation. This theoretical process connects black holes to light in a very indirect way, as the radiation they emit might be the only way we can ever detect their presence. So, while starlight might be swallowed by a black hole, the black hole itself can emit a faint glow of its own, offering a window into its inner workings. Hawking's work set the stage for a deeper understanding of black holes, but it wasn't the only breakthrough in this area. One of the most exciting developments in recent years has been the study of gravitational waves, ripples in space-time caused by the acceleration of massive objects. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting gravitational waves from the merger of two black holes. This discovery, which earned a Nobel Prize in Physics in 2017, confirmed the existence of black holes and provided an entirely new way of observing these otherwise invisible objects. Kip Thorne, a physicist and one of the pioneers of gravitational wave research, played a key role in the theoretical groundwork for understanding how black holes interact with one another. Thorne's contributions helped make it possible to predict the exact nature of the gravitational waves that would result from black hole mergers, and his work was crucial in interpreting the data collected by LIGO. When LIGO detected the gravitational waves from the merger of two black holes, it was like hearing the echoes of two cosmic giants colliding, a collision that sent out ripples through the very fabric of space-time. These breakthroughs in our understanding of black holes, starlight, and gravitational waves have changed the way we think about the end of a star's life. In the past, we thought of the star's death as the final chapter, a simple explosion followed by a dimming of light. But now we know that the death of a star can lead to the formation of something far more mysterious and complex. An object that warps space and time itself, absorbing everything around it, yet still offering a faint elusive glow through Hawking radiation. The connection between starlight and black holes also deepens our understanding of the universe's most extreme environments. The energy released in a supernova, the last great burst of light a star produces, can be immense, and it plays a key role in dispersing heavy elements into space. These elements are the building blocks of planets and life. The fate of the light from these dying stars, as it disappears into the black hole, serves as a reminder of the ever-evolving nature of the universe, where even the brightest stars must eventually make way for something even more mysterious and profound. In the end, the light we see from stars is a fleeting moment in their existence. It may shine brightly for billions of years, but once that light fades into a black hole, it is gone. Yet, the knowledge we gain from studying black holes and the light they consume continues to push the boundaries of our understanding. We're left with questions that may never fully be answered, but the beauty of science is in the pursuit itself, discovering how the universe works, one hidden mystery at a time. And as we continue to study black holes, starlight, and the forces that shape them, we inch closer to unraveling the most profound mysteries of space and time. When we look at the stars, we often think of them as solitary objects, shining in the vastness of space. However, many stars are not alone. In fact, the majority of stars in the universe exist in binary or even ternary systems, meaning they are part of a group, dancing together in an intricate cosmic ballet. In these multi-star systems, the gravitational pull of each star influences the others, creating fascinating interactions that affect their behavior, their light, and even their eventual fate. A binary star system consists of two stars that are bound together by gravity. They orbit around a common center of mass, known as the barycenter, which might be located between the two stars or closer to one of them, depending on their relative masses. These systems are incredibly common. In fact, about half of the stars we observe in the night sky are part of a binary system. Ternary systems, which contain 3 stars, are also not rare, though they are a bit more complex. When stars are in multiple systems like these, their interactions with one another can reveal much more than the sum of their individual light. The combined light from multiple stars creates a unique signature that astronomers can study. When we observe a binary or ternary system, the way the stars interact can tell us a great deal about the internal structure of each star. For example, by studying the brightness of these stars over time, we can measure how they move in their orbits, which tells us about their masses, their sizes, and even their temperatures. If the stars are close enough, their gravity can pull on each other in such a way that we can detect subtle changes in their positions and velocities. This process allows astronomers to determine important characteristics like the star's density, which would be impossible to measure if we were observing a single, isolated star. One of the most important figures in our understanding of binary star systems is the Dutch-American astronomer W. J. Luyten. In 1930, Luyten studied the binary system Luyten 726-8, one of the closest known binary systems to Earth. Located just about 8.6 light-years away, this system contains 2 faint red dwarf stars. Luyten's work in cataloguing stars like these helped to refine our understanding of stellar motion and how light from these systems could be used to learn about their properties. His observations demonstrated how binary star systems could be used to measure the masses of stars more accurately than ever before. Luyten's discoveries were foundational, showing us that even the faintest stars could reveal important information about the universe if we looked closely enough. But the interactions between stars don't just help us learn about their individual properties. In multi-star systems, the gravitational forces at play can distort the light we observe. These distortions can offer incredible insights into the nature of space-time itself. When 2 stars are in close orbit, Their mutual gravitational attraction causes a phenomenon known as gravitational lensing. This happens when the gravity of one star bends the light from the other, much like how a magnifying glass bends light. This effect can cause the light to appear brighter, distorted, or even multiple times, depending on the alignment of the stars. These distortions not only help us study the stars themselves, but also allow us to investigate the curvature of space-time around them. In some cases, the gravitational lensing effect can be so strong that it allows us to observe objects that would otherwise be invisible. For example, in certain binary or ternary star systems, the gravity of the stars can bend light from distant galaxies, magnifying them in a way that gives us a closer look at far-off objects in the universe. This allows astronomers to study galaxies that are millions, even billions, of light-years away simply by observing the lensing effect created by a nearby star. It's as if the stars are helping us peer deeper into the universe, giving us a clearer view of objects far beyond what our telescopes can directly detect. The study of multiple star systems also gives us valuable insights into the evolution of stars and the forces that shape them. For instance, in some binary systems, the stars are so close that they can exchange material through a process known as mass transfer. This occurs when one star expands and its outer layers spill over onto its companion, transferring mass between the two. This interaction can drastically alter the evolution of both stars. In some cases, it can lead to the formation of exotic objects like white dwarfs, neutron stars, or even black holes. By observing these interactions, astronomers can learn about the later stages of stellar evolution and the types of objects that can result from the death of a star. The light we observe from multi-star systems doesn't just tell us about the stars themselves, it also allows us to study the space between them. In these systems, the distances between stars can be vast, and the gravitational interactions that occur between them can create fascinating phenomena. Sometimes, the light from one star can be used to study the surrounding space, revealing the presence of interstellar gas, dust, or even unseen planets. These interactions are a reminder that stars are not isolated entities, but are part of a dynamic, interconnected universe, where gravity and light work together to reveal the structure of space itself. As we continue to explore binary and ternary star systems, we gain a deeper understanding of the forces at play in the universe. The combined light from these stars, the way their gravitational fields distort that light, and the interactions between the stars all provide us with valuable information about their composition, motion, and evolution. These systems serve as cosmic laboratories, allowing us to test theories of stellar physics and space-time in ways that would be impossible with a single star. The study of multi-star systems not only enriches our understanding of the stars themselves, but also offers us a window into the broader workings of the universe. From gravitational lensing that magnifies distant galaxies to the way stars interact in close orbits, these systems continue to be a rich source of discovery. As we observe the light from these stars, we're reminded that the universe is not just a collection of isolated objects, but a vast, interconnected web where every star, every system, and every piece of light is part of the greater cosmic dance. As we look up at the stars, we see their light streaming through the vastness of space, a cosmic beacon that illuminates the darkness of the universe. But what if that light is not just travelling through the empty void? What if, in fact, there's something invisible that's affecting the light we observe, bending it, distorting it, and altering the way we perceive the very stars themselves? This invisible force is known as dark matter, and it plays a crucial role in the way starlight reaches us. Dark matter, though it cannot be seen directly, exerts an undeniable influence on the universe. We know it exists because of its gravitational effects on visible matter. Without dark matter, the galaxies we observe would not have the structure we see today. Stars would fly apart, and galaxies would not remain bound together in the way they do. But while dark matter is essential in understanding the universe's large-scale structure, it also has a more subtle effect on the light we see from distant stars. One of the most fascinating ways dark matter interacts with light is through a phenomenon known as gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, such as a galaxy or cluster of galaxies, bends the path of light from a more distant object, like a star or galaxy. Normally, light travels in a straight line, but the gravitational field of dark matter can cause light to bend, just as a magnifying glass bends the light from a distant object. The result is that the light from a faraway star or galaxy can appear distorted, brighter, or in some cases even multiple times, creating a kind of cosmic magnification. Gravitational lensing allows astronomers to study distant stars, galaxies, and even black holes that might otherwise be too faint or too far to observe. But what's even more interesting is that dark matter itself is the primary source of the gravitational fields that cause this lensing. The light we see from stars far beyond the reach of our telescopes is often magnified by the gravitational influence of dark matter that lies between us and those stars. This means that dark matter is not just an invisible presence lurking in the background of the universe, but an active player in how we observe the cosmos. It's as if dark matter, though unseen, is helping us peer deeper into space, offering us glimpses of galaxies that would otherwise remain hidden. The first hints of dark matter's existence came from the work of Swiss astronomer Fritz Zwicky in the 1930s. While studying the Coma galaxy cluster, Zwicky noticed something peculiar. The galaxies in the cluster were moving much faster than they should have been, given the amount of visible matter present. Based on the laws of gravity, he concluded that there must be some invisible mass that was holding the galaxies together, something he called dark matter. At the time, Zwicky's theory was largely dismissed, but over the following decades, more and more evidence mounted to support the idea that dark matter was real. The effects of dark matter could be seen in the way galaxies rotated, in the movement of galaxy clusters, and in the bending of light through gravitational lensing. In recent years, the study of dark matter has advanced significantly, particularly with the help of cutting-edge research from institutions like CERN, the European Organisation for Nuclear Research. At CERN, scientists have been using particle accelerators to probe the fundamental nature of matter, and in doing so, they've made important strides in understanding how dark matter might interact with ordinary matter. Though dark matter has yet to be detected directly in laboratory experiments, researchers are getting closer to uncovering its elusive properties. Some theorists believe that dark matter could be composed of particles called WIMPs, or weakly interacting massive particles, which interact only through gravity and the weak nuclear force. If this is the case, it could explain why dark matter is invisible. It doesn't emit, absorb, or reflect light in the way ordinary matter does. But dark matter's interaction with light goes beyond just gravitational lensing. One of the most intriguing ideas in current astrophysical research is the possibility that dark matter could directly interact with photons, the particles of light. Some theories suggest that dark matter could be transparent to light, but could still influence it in subtle ways. For instance, certain types of dark matter might scatter light or even change the way it propagates through space. While this idea is still speculative, it raises fascinating questions about the relationship between light and the mysterious dark matter that pervades the universe. This potential interaction between dark matter and light could have profound implications for our understanding of the universe. If dark matter does interact with photons in previously unknown ways, it could reveal new insights into the fundamental nature of both dark matter and light itself. It could also provide a deeper understanding of the structure and evolution of the universe, offering clues to how galaxies, stars, and even the very fabric of space-time came into being. As we continue to explore dark matter's role in the cosmos, we are faced with a paradox. We know that dark matter is there because we can observe its effects on visible matter. But because dark matter doesn't interact with light in the way that normal matter does, it remains one of the great mysteries of modern physics. And yet, the more we learn about how dark matter bends, distorts, and even magnifies starlight, the more we begin to uncover about the universe's deepest secrets. The relationship between dark matter and starlight is a perfect example of how much we still have to discover about the universe. Even as we look at the stars, we are reminded that there is much more to the cosmos than meets the eye. Dark matter, with its invisible influence on the light from distant stars, is both a challenge and an opportunity for astronomers. As we continue to study its effects, we may unlock the key to understanding not just the universe's structure, but also the very nature of the forces that govern it. For now, the light we see from distant stars is a blend of the visible and the hidden, an intricate dance of photons and invisible forces that stretch across space and time. The more we study this light, the more we realize that the universe is full of mysteries, waiting for us to uncover them, one piece at a time. And dark matter, in its quiet, invisible way, is helping us do just that. When we look up at the night sky, we see countless stars, each shining with its own unique light. But what if I told you that not all of that light reaches us unaltered? The light from distant stars travels through vast expanses of space, passing through a complex web of gas, dust, and other materials before it finally reaches our eyes. The environments through which this light passes, particularly nebulae and the interstellar medium, play a significant role in shaping the light we observe. These environments, vast clouds of gas and dust, can absorb, refract, or scatter starlight, affecting how we perceive the stars and what we can learn from them. Nebulae, the colourful clouds of gas and dust we often associate with the birth of new stars, are particularly influential in this process. Some nebulae are dense enough to block light entirely, preventing us from seeing the stars behind them. Others, however, are more transparent, allowing some light to pass through while altering its colour or intensity. The way light interacts with these nebulae can tell us a great deal about the physical conditions within them. For instance, as starlight passes through a nebula, it can excite the atoms in the gas, causing them to emit their own light. This process, known as fluorescence, is what gives many nebulae their characteristic glowing colours. The interstellar medium, which consists of the gas and dust scattered between the stars in a galaxy, also has a significant impact on starlight. The medium itself is mostly composed of hydrogen and helium, but it also contains small amounts of heavier elements, as well as microscopic particles of dust. As light travels through this medium, it can scatter off these dust particles, causing the light to lose its sharpness and appear dimmer or redder. This effect, known as interstellar reddening, is one reason why distant stars often appear redder than they actually are. The dust in the interstellar medium absorbs some of the shorter, bluer wavelengths of light and scatters them, leaving behind the longer, redder wavelengths to reach us. John L. Gott III, a prominent astrophysicist, made important contributions to our understanding of the interstellar medium and its role in shaping the light we observe from stars. In his research, Gott studied how light passing through the interstellar medium is affected by the density and distribution of gas and dust. He showed that the properties of the medium, such as its temperature and the amount of dust it contains, play a crucial role in determining how much light is absorbed or scattered along the way. This research has helped astronomers develop more accurate models of star formation, as the light we observe from young stars often passes through these dense regions before reaching us. By studying how this light is altered, we can learn more about the conditions in these star-forming regions. Molecular clouds, which are cold, dense clouds of gas, are some of the most significant contributors to the obscuration of starlight. These clouds are the birthplaces of new stars, but they are also incredibly effective at blocking light. As starlight travels through these clouds, it can be absorbed by the gas, leaving behind only a faint trace of the light that originally emitted from the star. This process is crucial to our understanding of star formation, as the light from young stars that emerges from these clouds provides key insights into the conditions that lead to star formation. The fact that molecular clouds can block out most of the visible light from young stars has led astronomers to use other methods of detection, such as infrared observations, to study these regions more effectively. Infrared light can penetrate these clouds much more easily than visible light, allowing us to see through the dense gas and observe the formation of stars in real time. In addition to molecular clouds, interstellar dust plays a key role in the way light is scattered and absorbed in space. Chandra Wickramasinghe, an astronomer known for his work on interstellar dust, has contributed significantly to our understanding of how this dust affects starlight. Wickramasinghe's research has focused on the composition and distribution of dust particles in the interstellar medium and how these particles interact with light. He showed that interstellar dust is not uniform, but exists in varying densities across the galaxy. This variability can cause significant differences in the amount of light that reaches us from stars, depending on the path that light takes through space. Dust in the interstellar medium is composed of tiny particles that are just the right size to scatter light. When light passes through a dust cloud, it can cause the light waves to scatter in all directions, making the light appear dimmer and redder. This is similar to the way the sky appears blue during the day, because the shorter blue wavelengths of light are scattered more than the longer red wavelengths. In the case of stars, however, the opposite effect occurs, and the light becomes redder as it passes through the dust. This scattering can make it difficult for astronomers to accurately determine the distance to distant stars, as the amount of reddening can vary depending on the amount of dust in the path of the light. These interactions between light, dust, and gas offer invaluable insights into star formation and the larger structure of our galaxy. By studying how starlight is affected by the environments it passes through, astronomers can learn about the physical properties of nebulae, molecular clouds, and the interstellar medium. These regions are the birthplace of new stars, and the light that emerges from them provides crucial information about the conditions under which stars form. The study of this light is also key to understanding the overall structure of our galaxy, as it helps astronomers map the distribution of gas, dust, and other materials throughout space. For example, the light from stars passing through the interstellar medium can reveal the presence of large-scale structures in the galaxy, such as spiral arms or dense star-forming regions. These structures are shaped by the gas and dust that fill the space between stars, and the way light interacts with these materials can help us understand how the galaxy has evolved over time. By observing how the light from stars changes as it passes through these regions, astronomers can begin to piece together the larger story of the galaxy's formation and growth. In a way, starlight is more than just a beacon of light in the darkness. It is a messenger that carries with it information about the environments it passes through. The way it is affected by the gas and dust in the interstellar medium offers us a glimpse into the conditions that give rise to stars and galaxies. As we continue to study these interactions, we are not only learning more about the stars themselves, but also uncovering the hidden forces that shape the universe. Whether it's through the study of molecular clouds, interstellar dust, or the light that filters through them, the story of starlight is ultimately a story of discovery, one that takes us closer to understanding the very building blocks of the cosmos. Imagine a vast galaxy, millions or even billions of light years away. Now picture that galaxy's light reaching us, but not in a straight line. Instead, the light bends, distorts, and even magnifies as it travels through space. This fascinating phenomenon, known as gravitational lensing, occurs when the light from distant objects, like stars or galaxies, passes near a massive object, such as another galaxy or a black hole. The massive object's gravity warps space-time itself, bending the path of light in a way that magnifies and distorts the image we observe. Gravitational lensing is one of the most incredible predictions of Einstein's theory of general relativity, which he first introduced in 1915. General relativity tells us that massive objects, like stars and galaxies, curve the fabric of space-time around them. This curvature not only affects the motion of objects within space, but also bends the path of light travelling through it. Einstein's equations showed that light should bend around massive objects, and this was a completely revolutionary idea at the time. But it wasn't until 1920 that this theory was confirmed in a groundbreaking experiment led by British astronomer Arthur Eddington. Eddington's famous experiment observed a total solar eclipse, during which the light from stars passing behind the Sun was measured. According to Einstein's predictions, the Sun's massive gravitational field should cause the starlight to bend as it passed near the Sun. Eddington and his team observed just that. The stars' positions appeared slightly shifted due to the bending of their light, confirming Einstein's theory and showing that gravity could indeed bend light. This was the first real confirmation that space-time was not the static, unchanging stage that we once thought, but a dynamic, flexible fabric that could be distorted by the presence of mass. Fast forward to today, and gravitational lensing has become a powerful tool for astronomers to study the cosmos in ways that were once impossible. When light from a distant galaxy passes through the gravitational field of an intervening galaxy, the light is bent, creating a distorted image. Sometimes, this distortion is so extreme that it forms multiple images of the same object, or even a ring of light, known as an Einstein ring. These distorted images are like cosmic magnifying glasses, allowing us to peer deeper into the universe, revealing hidden structures that we otherwise would not be able to observe. One of the most exciting uses of gravitational lensing is its ability to reveal the mysterious presence of dark matter. Dark matter is an invisible substance that does not emit, absorb, or reflect light, making it impossible to detect directly. However, we know it exists because of its gravitational effects on visible matter. Gravitational lensing allows us to detect dark matter indirectly by observing how it bends and distorts the light from background objects. When light passes through a galaxy or a galaxy cluster, the mass of the dark matter within those objects can distort the light, providing a glimpse into its distribution. This is how scientists have been able to map the presence of dark matter in galaxy clusters and gain insight into its role in shaping the universe. The work of astronomer Srinivas Kulkarni has been instrumental in advancing our understanding of gravitational lensing. Kulkarni's research has focused on using lensing to study some of the most distant and faint objects in the universe. By observing how light is bent by massive objects, he and his colleagues have been able to identify galaxies and other cosmic structures that would otherwise be invisible to us. Through this technique, astronomers have been able to study objects that are located billions of light years away, unlocking new insights into the early universe and its evolution. Gravitational lensing also offers a fascinating opportunity to observe objects that are too far to reach with traditional methods. For instance, in the case of supernovae, exploding stars that are incredibly bright but often occur at vast distances, lensing can act as a magnifying lens, bringing the distant explosion closer and allowing us to study it in much greater detail. These lensed supernovae appear brighter and more detailed than they would normally, giving astronomers an unprecedented opportunity to learn about the explosion's mechanics, its composition, and its aftermath. In some cases, gravitational lensing has even helped astronomers study the structure of the galaxies hosting these supernovae, allowing us to see details that would otherwise be impossible to detect. The power of gravitational lensing lies in its ability to reveal hidden objects and structures, magnifying the light from distant stars, galaxies, and other cosmic phenomena. It's like a cosmic magnifying glass, enabling us to study the universe with greater precision and detail than ever before. Through lensing, we can peer deeper into the heart of galaxy clusters, uncover the presence of dark matter, and study the distant past of the universe itself. Without this phenomenon, many of the objects and structures we've come to understand, such as the existence of dark matter and the details of galaxy formation, would remain hidden. Gravitational lensing has transformed the way we observe the universe. It's a phenomenon that allows us to study distant objects that would otherwise be beyond our reach, providing us with a deeper understanding of the structure and evolution of the cosmos. The bending of starlight has opened up new frontiers in astronomy, offering us insights into the unseen and the unexplored, from the bending of light around massive galaxy clusters to the study of dark matter and the faintest galaxies. As our ability to study gravitational lensing improves, so too does our ability to understand the vast, intricate universe that surrounds us. In many ways, gravitational lensing is a reminder of how much we still have to discover. Even though we can't see dark matter or some of the most distant objects in the universe with our eyes, lensing allows us to detect their presence and study them in remarkable detail. It's as if the universe is giving us a glimpse of its secrets through the distortion of light, challenging us to look deeper, to question more, and to understand the true nature of the cosmos. As we look at the night sky, we see stars, galaxies, and nebulae, each one shining with the light that has travelled across unimaginable distances to reach us. But the light we observe is not always as simple as it seems. In fact, the very nature of that light, and how it changes as it moves through space, holds the key to understanding the most profound mysteries of the universe, like its expansion. The phenomenon known as redshift plays a crucial role in unlocking these mysteries. Redshift occurs when the light from an object, such as a star or galaxy, is stretched to longer wavelengths, shifting it toward the red end of the spectrum. This happens when the object is moving away from us. In contrast, if an object is moving toward us, the light is compressed, shifting it toward the blue end of the spectrum, a phenomenon called blue shift. These shifts are like cosmic speedometers, allowing us to measure the motion of stars, galaxies, and other objects in the universe. But what really makes redshift so powerful is how it helps us measure the expansion of the entire universe itself. This connection between redshift and the expanding universe was first made clear by the American astronomer Edwin Hubble in the early 1920s. Hubble, while studying galaxies, noticed something remarkable. He found that the farther away a galaxy is from us, the faster it appears to be moving away. This was a stunning revelation. It suggested that the universe was not static but was, in fact, expanding. Hubble's observations led to what we now call Hubble's law, which states that the velocity at which a galaxy is receding from us is directly proportional to its distance. Essentially, the farther a galaxy is, the faster it is moving away. This relationship between distance and velocity is observed through the redshift of the light from distant galaxies. Hubble's discovery was monumental because it provided the first evidence for what would become one of the cornerstones of modern cosmology. The universe is expanding. This means that the space between galaxies is stretching, causing the light from those galaxies to be stretched as well, shifting it toward longer wavelengths. Redshift became the key to measuring this expansion, and it fundamentally changed our understanding of the universe's history. It wasn't just that the galaxies were moving away from us, it was that space itself was expanding, stretching the very fabric of the universe. But there's more to the story of the expanding universe, and it has to do with something even more mysterious than redshift: dark energy. In the late 20th century, astronomers made another astonishing discovery. In the 1990s, two independent teams of scientists, led by Saul Perlmutter and others, observed distant supernovae, exploding stars that are often used as cosmic beacons to measure distances. To their surprise, they found that these supernovae were farther away than expected. What's more, the galaxies they came from were receding at a faster rate than predicted by Hubble's law. This unexpected acceleration in the rate of expansion led to the conclusion that some unknown force, which came to be known as dark energy, was driving the accelerated expansion of the universe. Dark energy is believed to make up around 70% of the total energy content of the universe, yet it remains one of the most enigmatic aspects of modern physics. Unlike matter, which exerts a gravitational pull, dark energy seems to have the opposite effect. It accelerates the expansion of space. This discovery was so profound that in 2014, Saul Perlmutter, along with his colleagues, was awarded the Nobel Prize in Physics for their role in uncovering the existence of dark energy and its impact on the universe's expansion. The connection between redshift and the expansion of the universe also has a profound effect on how we understand the age of the universe. By measuring the redshift of galaxies, astronomers can trace the history of the universe back to its very beginning, to the moment of the Big Bang. As light from distant galaxies shifts toward the red end of the spectrum, it tells us not only how far away the galaxy is, but also how long that light has been travelling toward us. This gives us a cosmic clock, allowing us to measure the age of the universe by studying the light from distant galaxies and supernovae. In essence, redshift has become one of the most important tools in modern cosmology, offering a window into the past of the universe. By studying the redshift of galaxies, we can learn about the rate at which the universe expanded in the past, helping us piece together the timeline of cosmic events. This includes determining how long it took for galaxies to form, how the rate of expansion has changed over time, and what role dark energy has played in the acceleration of that expansion. Redshift, along with the discovery of dark energy, has allowed scientists to create more accurate models of the universe's evolution. What's particularly fascinating is how these discoveries continue to shape our understanding of the universe's future. If the expansion of the universe continues to accelerate, driven by dark energy, the universe will eventually reach a state where galaxies will be so far apart that the light from distant stars will no longer reach us. In a sense, redshift not only helps us look back in time to the early universe, but also gives us a glimpse of the universe's future, where galaxies will be stretched apart so much that they will become invisible to us. As we look further into the cosmos, we continue to refine our understanding of redshift and the expansion of the universe. New telescopes and observational techniques are allowing us to measure redshift with greater precision, helping us uncover the details of how the universe has evolved and how it will continue to change. Through redshift, we're able to trace the history of the universe, from its violent birth in the Big Bang to its current state, and perhaps into its distant future. The study of redshift is also allowing us to explore some of the most fundamental questions in cosmology. What is dark energy? What is the true nature of the universe's expansion? And how will the universe continue to evolve? These are questions that may take decades, if not centuries, to answer. But one thing is clear: redshift has opened a door to understanding the very nature of the cosmos, offering us a glimpse into the universe's past, present, and future. The light we observe from distant stars is not just a simple beacon in the night sky. It is a messenger, carrying with it the stories of the universe's expansion, from the early moments of the Big Bang to the current era of accelerating growth. Through the redshift of that light, we can unlock the secrets of the universe and begin to piece together the most profound questions in science. Whether we're studying the motion of galaxies, the role of dark energy, or the age of the universe itself, redshift remains one of the most powerful tools in our quest to understand the cosmos. The journey of Starlight doesn't just begin when we first spot a star glimmering in the night sky. In fact, to truly understand the light that reaches us today, we need to look all the way back to the very beginning of the universe. The light we see today, whether it's from a distant galaxy or a nearby star, carries with it the imprints of the universe's early moments, right after the Big Bang. Understanding how Starlight's early emissions reveal the birth of the universe is one of the most profound questions in cosmology. After the Big Bang, which occurred approximately 13.8 billion years ago, the universe was a hot, dense soup of particles. Over time, as the universe expanded and cooled, atoms began to form and light, once trapped by the dense particles, was finally able to travel freely. This moment, known as the recombination, occurred about 300,000 years after the Big Bang, marking the first time that light could move unhindered through the vast expanse of space. The light that was released during this time, however, wasn't the bright, visible starlight we see today. Instead, it was a faint glow in the microwave part of the spectrum, now known as the cosmic microwave background radiation. The cosmic microwave background radiation, often abbreviated as CMB, is one of the most important pieces of evidence supporting our understanding of the Big Bang. The idea of such radiation was first predicted by physicist George Gamow and his colleagues in the 1940s. They theorized that the universe in its early moments was so hot that it would have emitted light in the form of a thermal radiation, which would eventually stretch into the microwave wavelengths as the universe expanded and cooled. Gamow's predictions set the stage for a discovery that would change our understanding of the cosmos. In 1965, two American scientists, Arno Penzias and Robert Wilson, accidentally stumbled upon this very radiation while working with a radio telescope. They were initially confused by the persistent background noise they detected, but soon realized that it was the cosmic microwave background radiation, leftover light from the Big Bang itself. This discovery was groundbreaking. It confirmed that the universe had a beginning, and the faint glow that permeates space today is a direct remnant of that momentous event. What makes the cosmic microwave background radiation so significant is that it provides a snapshot of the early universe. By studying the patterns and temperature fluctuations in this radiation, astronomers can learn about the conditions that existed just moments after the Big Bang. The CMB offers a detailed map of the universe's early structure, showing how matter was distributed when the universe was just a few 100,000 years old. These tiny fluctuations in the CMB have been used to build models of the universe's expansion and evolution, shedding light on the forces that shaped the cosmos. But the story doesn't end there. The study of starlight in the context of the Big Bang has also sparked debates about whether our universe is the only one that exists. One of the most intriguing ideas that has emerged in recent years is the theory of the multiverse, the idea that our universe might be just one of many, each with its own set of physical laws and properties. Some theories suggest that the light we see today might be a mere fraction of a much larger cosmic structure. In a multiverse, the Big Bang we experience could have been just one of many such events, each creating its own universe, with varying outcomes. This idea of the multiverse pushes the boundaries of our understanding of starlight. If our universe is part of a larger multiverse, then the light we observe from distant stars and galaxies might be influenced by the conditions in neighbouring universes. Some theories suggest that the way light behaves in our universe could be connected to the fundamental properties of other universes, ideas that challenge our very concept of reality. While the multiverse theory is still speculative and unproven, it opens up exciting possibilities for how starlight might reveal more than just our own universe's history. At the forefront of understanding the Big Bang and the evolution of the universe is physicist James Peebles. Peebles, whose work in cosmology earned him a Nobel Prize in Physics in 2019, has been instrumental in developing models of the universe that incorporate starlight. His contributions to the understanding of the cosmic microwave background radiation and the role of dark matter and dark energy in the universe's evolution have reshaped the way we think about the Big Bang. Peebles' work has provided crucial insights into the expansion of the universe, the formation of galaxies, and the conditions under which stars and galaxies began to form. Peebles and others have shown that by studying the light from distant stars and galaxies, we can trace the universe's history from the very beginning. The earliest light we observe, the cosmic microwave background, provides a snapshot of the universe's infancy, while the light from more recent stars and galaxies tells us about the formation of galaxies, stars, and planetary systems. Through the study of starlight, we can begin to piece together the timeline of the universe, from its explosive birth to its current state. Yet, not all cosmologists agree on the standard Big Bang model. Some alternative theories, such as the cyclic model, offer different interpretations of the universe's creation. The cyclic model suggests that the universe undergoes an endless series of expansions and contractions, with each Big Bang being followed by a big crunch, where the universe collapses back in on itself before starting the cycle again. In this model, the light from the universe's past might be part of a much longer cyclical pattern of creation and destruction. While this idea is still speculative, it offers a new perspective on the role of starlight in understanding the universe's origin. Regardless of which theory we subscribe to, the study of starlight is essential in uncovering the mysteries of the universe's creation. The light we observe today, whether it's from the cosmic microwave background or from distant stars and galaxies, carries with it the imprints of the universe's early moments. Starlight has the power to reveal the forces that shape the universe and to help us understand its evolution, from the Big Bang to the present day. As we continue to explore the universe through the lens of starlight, we are uncovering more about our own origins and the broader structure of the cosmos. The study of starlight, from its earliest emissions to its role in the expansion of the universe, is one of the most profound ways we can connect with the universe's past. And as our understanding of starlight deepens, so too does our understanding of the universe itself, offering new insights into the nature of time, space, and the very fabric of reality. The life of a star is nothing short of extraordinary. From its quiet beginnings as a cloud of gas and dust, it embarks on a journey of transformation, eventually reaching an explosive end. This process, which takes millions or even billions of years, is the story of stellar evolution, a fascinating cycle that shapes the stars and the elements in the universe. Stars are born in the vast, dark clouds of gas and dust scattered throughout space. These clouds, known as nebulae, are the cosmic nurseries where stars take shape. Under the influence of gravity, regions of the nebula begin to collapse inward. As the gas and dust particles are pulled together, the material heats up, forming a protostar, a dense, hot core that is the first stage of a star's life. At this point, the protostar is still too cool to begin nuclear fusion, the process that powers stars and makes them shine. But the energy generated by the collapse and the pressure inside the protostar is enough to start heating the surrounding gas, creating a faint glow of starlight. The path from protostar to a fully formed star is not a straight line. In fact, it takes millions of years for a star to reach its full brightness. As the protostar contracts, its core continues to heat up until it eventually reaches temperatures and pressures high enough to initiate nuclear fusion. This is the moment when the star truly begins its life, shining brightly with energy produced by the fusion of hydrogen atoms into helium. This process releases a tremendous amount of energy in the form of light, and it is this light that allows astronomers to begin studying stars in detail. The study of stellar structure, particularly how stars evolve and how their internal processes work, owes much to the pioneering work of physicists like Sir Arthur Eddington. In the early 20th century, Eddington developed models that explained how stars generate energy through fusion in their cores. His work helped to clarify the balance between the inward pull of gravity and the outward pressure from the fusion reactions inside a star, a balance that keeps stars stable for most of their lives. Eddington's contributions were crucial in shaping our understanding of how stars shine and how they evolve over time, laying the foundation for modern astrophysics. As stars continue to burn hydrogen in their cores, they eventually exhaust the hydrogen fuel. When this happens, the star enters a new phase of its life, expanding into a red giant. In this phase, the outer layers of the star begin to expand, and the star becomes much larger and cooler. Despite the cooler surface temperature, the star shines more brightly due to its enormous size. The red giant stage is a critical turning point in a star's life, marking the beginning of its inevitable transition into something more explosive. When the core of a red giant runs out of hydrogen, it starts to contract and heat up, while the outer layers expand and cool. This triggers a series of fusion reactions, where helium atoms are fused into heavier elements like carbon and oxygen. The star begins to shed its outer layers, creating a nebula of gas and dust in the process. What remains is the hot, dense core, which will eventually become a white dwarf. This is the end of the road for stars like our Sun, which don't have enough mass to end their lives in a more dramatic fashion. However, for stars that are much more massive than the Sun, the story doesn't end with a white dwarf. Instead, these massive stars continue to fuse heavier and heavier elements until they can no longer sustain the pressure needed to keep their cores stable. When this happens, the core collapses under the weight of its own gravity, and the outer layers are blown off in a cataclysmic explosion known as a supernova. This explosion is one of the most powerful events in the universe, releasing an immense amount of energy and outshining entire galaxies for a brief period of time. The light from a supernova is a spectacular sight, and it provides astronomers with valuable information about the star's final moments. A supernova explosion creates heavy elements like iron, nickel, and gold, which are then scattered across space. These elements become part of the material that eventually forms new stars, planets, and even life itself. In this way, the death of a massive star becomes a critical part of the ongoing cycle of cosmic creation. The explosion of starlight in a supernova is not just the end of one star, it's the birth of new elements that will go on to form the building blocks of the next generation of stars and planets. The study of supernovae and their light has also allowed astronomers to gain insights into the age and size of the universe. By measuring the brightness of supernovae and how they change over time, astronomers can calculate how far away these stars are, helping to measure the rate of expansion of the universe. This connection between stellar explosions and the history of the universe is one of the many ways that starlight has allowed us to unravel the mysteries of the cosmos. From the quiet beginnings of a protostar to the explosive end of a supernova, the life cycle of a star is a complex and fascinating process. As stars evolve, their light provides us with the tools to study their internal workings, their size, their age, and even the forces that shape the universe. The starlight that we see today is not just the product of nuclear fusion. It is a glimpse into the life and death of stars, a testament to the incredible processes that govern the universe. Stellar evolution, from protostar to supernova, is not just a tale of individual stars, it is the story of the universe itself. The elements that make up our planets, our bodies, and everything we know were forged in the hearts of stars. Their light, from the very beginning of their lives to their explosive ends, is the key to understanding not just the stars themselves, but the universe as a whole. The starlight we observe today is not just a faint glimmer in the sky, it is a record of the past, a window into the processes that have shaped the cosmos, and a reminder of the continuous cycle of creation and destruction that drives the universe forward. When we look up at the night sky, we see stars that have been shining for millions or even billions of years, their light travelling across vast distances to reach us. But starlight does more than just illuminate the night sky. It also helps us discover new worlds that orbit stars far beyond our own solar system. These worlds, known as exoplanets, have been a focus of intense scientific curiosity, and starlight has become one of the most powerful tools for uncovering them. One of the most effective methods astronomers use to detect exoplanets is the transit method. This technique relies on the observation of starlight as a planet passes in front of its host star, from our perspective here on Earth. As the planet crosses the star's face, it causes a small but measurable dip in the star's brightness. This dimming occurs because the planet blocks a tiny fraction of the star's light, and by carefully monitoring this change, astronomers can detect the presence of an exoplanet, even though the planet itself is not visible. The transit method has revolutionized our ability to find exoplanets. When a planet transits its star, the amount of light that dims depends on the planet's size and the alignment of its orbit. Larger planets block more light, creating a more noticeable dip, while smaller planets cause smaller dimming. By measuring the amount of dimming and the time between transits, astronomers can calculate the planet's size, orbit, and distance from its star. This method has been instrumental in discovering thousands of exoplanets, including some that may be similar in size and temperature to Earth. One of the most significant contributions to the search for exoplanets came from the Kepler Space Telescope, launched in 2009. Kepler was specifically designed to detect exoplanets using the transit method. Over the course of its mission, Kepler monitored the brightness of over 100,000 stars searching for the telltale signs of planets passing in front of them. Kepler's observations led to the discovery of more than 2,000 exoplanets, including many that are in the so-called habitable zone of their stars, where conditions might be just right for liquid water to exist, an essential ingredient for life as we know it. Kepler's discoveries have opened up new frontiers in our understanding of planetary systems. For example, it revealed that planets come in a wide range of sizes, from small rocky worlds like Earth to gas giants much larger than Jupiter. It also showed that exoplanets are incredibly common, with most stars in the Milky Way likely hosting at least one planet. Kepler's success in finding exoplanets has not only expanded our knowledge of the universe but has also raised a tantalizing question. Are any of these distant planets capable of supporting life? This brings us to the concept of biosignatures, indicators of life that we might detect in the atmospheres of exoplanets. Just as Earth's atmosphere contains oxygen and methane, which are produced by life, astronomers are looking for similar signs on distant planets. If an exoplanet has an atmosphere with gases like oxygen, methane or carbon dioxide in certain combinations, it could be a sign that life is present. These gases can interact with starlight in distinct ways, and by analysing the spectrum of light that passes through a planet's atmosphere during a transit, astronomers can search for these potential biosignatures. The study of biosignatures is still in its early stages, but it's one of the most exciting aspects of exoplanet research. With more advanced telescopes and instruments, astronomers are becoming better equipped to analyse the starlight that passes through distant planets' atmospheres. For instance, the James Webb Space Telescope, which is set to launch soon, will have the ability to study the atmospheres of exoplanets with unprecedented detail. Its advanced instruments will allow scientists to search for the chemical signatures of life in the atmospheres of planets, in the habitable zones of distant stars, expanding our search for life beyond Earth. The role of starlight in studying exoplanets doesn't end with the detection of planets and biosignatures. Starlight also plays a crucial role in understanding the environments of these planets, particularly their atmospheres and their potential for habitability. The amount of light a planet receives from its star, its stellar flux, determines its surface temperature and whether liquid water can exist on its surface. By studying the starlight that reaches an exoplanet, astronomers can learn about the planet's climate, its potential for hosting life, and whether it has the conditions necessary for life to thrive. In recent years, the Transiting Exoplanet Survey Satellite, TESS, has become another key player in the search for exoplanets. Launched in 2018, TESS is designed to survey nearly the entire sky, searching for planets orbiting the brightest stars in our neighbourhood. TESS is continuing the work that Kepler began, discovering new exoplanets and expanding our understanding of how planets form and evolve. By observing the starlight of nearby stars, TESS is helping to identify planets that could be candidates for future study, including those that are located in the habitable zone of their stars. TESS's mission is not just about discovering new exoplanets, it's also about refining our understanding of planetary systems. By studying how starlight interacts with planets, astronomers can gain insights into the planet's atmospheres, magnetic fields, and even their potential to support life. With more data from TESS and upcoming missions, we will be able to map the diversity of planetary environments across the galaxy and better understand the conditions that might allow life to flourish elsewhere. The search for exoplanets is one of the most exciting areas of modern astronomy, and starlight plays a pivotal role in this quest. Through the careful study of how starlight is affected by planets, whether by the dimming caused by a planet transiting its star, by the chemical signatures in a planet's atmosphere, or by the light that reaches us from distant worlds, we are unlocking the secrets of the universe's hidden planets. With missions like Kepler, TESS, and the James Webb Space Telescope, we are closer than ever to answering one of humanity's most profound questions. Are we alone in the universe? As we continue to observe starlight from planets beyond our solar system, we are not just discovering new worlds, we are gaining a deeper understanding of the universe itself and our place within it. Whether it's searching for signs of life, studying the atmospheres of distant planets, or simply marvelling at the diversity of planetary systems, starlight is our guide, leading us to new frontiers in the search for other Earths and the possibility of life beyond our own planet. As we stand on the edge of discovery, the future of starlight studies promises to open new frontiers in our understanding of the universe. With advances in technology, innovative scientific instruments, and new theories that challenge our perceptions of space and time, we are on the verge of a new era in astronomy. The starlight that has guided our understanding of the cosmos for centuries will continue to shine a light on even deeper mysteries, but now we have the tools to study it with more precision and clarity than ever before. One of the most exciting developments in the study of starlight is the launch of the James Webb Space Telescope, or JWST, set to revolutionize our ability to study the universe. Planned for launch in 2021, this telescope will be the most powerful space telescope ever built, surpassing even the Hubble Space Telescope. Unlike Hubble, which primarily observes visible and ultraviolet light, JWST will focus on infrared light, allowing it to peer through cosmic dust and study distant stars and galaxies in unprecedented detail. This ability to see through the dust of space will be invaluable in studying star formation, the early universe, and the atmospheres of exoplanets. JWST will allow us to study starlight from the very beginnings of the universe, tracing the light emitted by the first stars that formed just a few 100 million years after the Big Bang. With its unprecedented sensitivity to infrared wavelengths, JWST will give us a glimpse of stars and galaxies that are so far away their light has been stretched over billions of years. This will provide us with a clearer picture of the universe's early stages, from its birth to the development of the first galaxies, stars, and black holes. In addition to space-based observatories like JWST, ground-based observatories are also advancing at an impressive pace. The extremely large telescope under construction in Chile is poised to be the world's largest optical telescope. With a primary mirror over 39 meters in diameter, it will allow astronomers to capture sharper images of distant stars, galaxies, and other cosmic phenomena. The immense size of its mirror will enable it to collect more light, providing much greater sensitivity and resolution than any telescope currently in operation. Coupled with these advancements in hardware are significant improvements in spectroscopic techniques. Spectroscopy allows astronomers to break down light into its component colors, or wavelengths, providing detailed information about the properties of stars, galaxies, and planets. New spectroscopic instruments are being developed that will allow astronomers to gather more detailed data than ever before. For example, high-resolution spectrographs will be able to analyze starlight with incredible precision, allowing us to study the chemical composition, temperature, and motion of stars in unprecedented detail. The advancement of artificial intelligence, AI, is also playing a critical role in revolutionizing starlight analysis. With the massive amounts of data generated by modern telescopes and observatories, AI is helping astronomers to process and analyze this data more efficiently. Machine learning algorithms are being used to detect patterns in starlight, identify exoplanets, and even predict stellar behavior. AI can quickly sift through terabytes of data, identifying anomalies or interesting features that might have otherwise gone unnoticed. This ability to process large data sets is crucial for the future of astronomy, as it allows scientists to make discoveries faster and more accurately than ever before. As we study starlight with these new tools, we're also exploring new theories that could reshape our understanding of the universe. One of the most intriguing ideas that has emerged in recent years is the theory of quantum gravity, which attempts to reconcile the seemingly incompatible realms of general relativity and quantum mechanics. In the search for a unified theory of everything, quantum gravity may offer insights into the nature of space-time itself and how starlight interacts with the fabric of the universe. The study of starlight could potentially reveal clues about the quantum nature of gravity, helping us understand how gravity works on the smallest scales. In addition to quantum gravity, dark matter and dark energy remain among the greatest unsolved mysteries in modern physics. While we cannot directly observe dark matter, its gravitational influence on visible matter is apparent. Studying how starlight is affected by dark matter could provide key insights into its properties. Similarly, dark energy, the mysterious force that is accelerating the expansion of the universe, may have subtle effects on starlight as it travels across space. As we refine our understanding of these invisible forces, starlight could offer indirect clues about their nature, helping to answer some of the most fundamental questions in cosmology. Another exciting area of exploration involves cosmic inflation, the rapid expansion of the universe in the first moments after the Big Bang. Theories of inflation suggest that the universe grew exponentially in size, stretching space itself and imprinting subtle patterns on the cosmic microwave background radiation. These imprints, known as cosmic perturbations, can be detected in the light that reaches us today, and studying them could provide crucial insights into the nature of the early universe. Advances in technology will allow us to probe these cosmic imprints with greater precision, furthering our understanding of the origins of the universe and the fundamental forces that shaped it. As we look to the future, the potential breakthroughs in starlight studies are truly exciting. The tools we have today, space telescopes like the James Webb Space Telescope, ground-based observatories, and advanced spectroscopic techniques, are already opening up new avenues of exploration. With the help of artificial intelligence, we are processing data faster and more accurately than ever before, allowing us to make discoveries that were once beyond our reach. And as new theories in quantum gravity, dark matter, and cosmic inflation continue to unfold, starlight will remain a key tool in unlocking the secrets of the universe. In the coming years, we may see discoveries that challenge our current understanding of space, time, and the nature of the cosmos. New insights into starlight and the forces that shape it could lead to paradigm shifts in our understanding of everything from the smallest particles to the largest structures in the universe. As we continue to push the boundaries of our knowledge, one thing is certain: starlight will remain our guide, illuminating the mysteries of the universe and helping us answer some of the most profound questions in science. For as long as humanity has existed, we've looked up at the stars and wondered. Starlight, with its soft glow and distant origins, has captured our imagination, becoming a symbol of mystery, beauty, and the vastness of the universe. It's no wonder that for millennia, starlight has played a central role not only in scientific inquiry, but in the realms of poetry, art, and philosophy. It has been a source of both wonder and contemplation, inspiring countless generations to ponder their place in the cosmos. There's something deeply mystical about starlight. When we gaze at a distant star, we are looking at light that may have travelled for millions, even billions, of years to reach us. In a very real sense, we are looking into the past, at a moment in time that has long since passed, yet it's still present in the form of light. It's almost as if starlight acts as a bridge between the ancient cosmos and our present selves, connecting us to the universe in a way that feels both timeless and profound. The light we see may be coming from a star that no longer exists, its energy having travelled across unimaginable distances to reach us, and yet its message remains. In this way, starlight links us not just to the stars but to the entire history of the universe, offering us a glimpse of the past while we stand in the present. The psychological impact of observing starlight cannot be overstated. From childhood wonder to adult reflection, the stars have always had a special hold on our minds and hearts. They represent the unknown, the infinite, and the unexplored. There's something deeply humbling about standing beneath a night sky full of stars, realizing that we are just a tiny part of a much larger universe. In that moment, starlight has the power to make us feel both incredibly small and incredibly connected to the universe around us. It reminds us of our curiosity, our desire to explore, and our place in the grand scheme of things. Throughout history, the stars have guided explorers and navigators, provided a sense of direction, and served as markers of time. Today, they continue to fuel our sense of wonder, inspiring new generations of scientists, philosophers, and dreamers. Starlight also plays a significant role in the world of art and literature. For poets, artists, and musicians, the stars have always been a symbol of something greater than themselves, a representation of beauty, longing, and the mysteries of existence. From the ancient Greek myths to modern poetry, starlight has been an enduring motif. Writers like William Shakespeare and John Keats wrote of the stars as symbols of eternal beauty and love. In modern times, starlight continues to inspire contemporary artists and musicians, evoking emotions that words alone sometimes cannot capture. Whether it's a painting of a starry night, a song that describes the vastness of space, or a poem that contemplates the meaning of life, starlight has the power to evoke deep, emotional responses that connect us to something beyond ourselves. Even in the realm of science, starlight plays a crucial role in shaping our understanding of the universe. It has guided astronomers in their quest to unlock the secrets of the cosmos, helping them map out the structure of galaxies, measure the distance between stars, and uncover the mysteries of black holes, supernova, and exoplanets. Every discovery about starlight adds another layer to our knowledge, revealing more about the origins of the universe, the nature of space-time, and the possibility of life beyond our planet. In this way, starlight not only illuminates the physical universe, but also illuminates our understanding of the very fabric of existence itself. And yet, despite all the progress we've made in our understanding of starlight, there is still much we don't know. New technologies such as the James Webb Space Telescope and the upcoming generation of ground-based observatories will soon allow us to study starlight with greater precision than ever before. We'll be able to peer deeper into space, observe the earliest moments of the universe, and perhaps even discover new forms of life on distant exoplanets. As we advance our technological capabilities, starlight will continue to be our guide, shedding light on the darkest corners of the cosmos. One of the most exciting prospects for the future of starlight studies lies in the exploration of other galaxies and the detection of light from the very first stars that formed after the Big Bang. By studying this ancient light, we may be able to learn more about the origins of the universe, the formation of the first galaxies, and the mysterious forces that shape the cosmos. The study of starlight from distant stars and galaxies is likely to continue expanding our understanding of the universe's evolution, offering insights into the fundamental nature of time, space, and matter itself. As we reflect on the journey of starlight, from its creation in the cores of distant stars to its arrival here on Earth, we can't help but marvel at the profound impact it has had on our civilization. It has inspired poets, scientists, artists, and dreamers for millennia, connecting us to something far greater than ourselves. In many ways, starlight is more than just light. It is a symbol of human curiosity, creativity, and the relentless pursuit of knowledge. It reminds us that, no matter how much we learn, the universe will always hold more mysteries to discover. So, the next time you gaze up at the stars, take a moment to appreciate the journey that the light has taken to reach you. Think about the stars that have burned for billions of years, their light travelling across the vast expanse of space, carrying with it the history of the universe. Let that light inspire you, just as it has inspired countless generations before. And as we continue to study starlight and explore the cosmos, we are reminded that the universe is not just out there, beyond our reach. It is also within us, lighting the way forward into the unknown.